Thank you, Syed, for covering almost everything, the entire end-to-end pipeline of Indic Web to Web models. I will touch upon the role of language models in ASR, and yeah, I will try to briefly go through what language models are, why do we need them, where do we integrate it in our pipeline, and we'll see how much improvement do we get by including language models. Yeah, I will be taking questions at the end, but do keep posting on the Zoom also. Yeah, so how do we perceive speech? Speech is both a composition of acoustic features and language features. And the question is, by building just a acoustic model, how much of the language characteristic can we capture from it? Interestingly, we do capture a lot of language characteristics, but is it enough? In what cases it's not? So we'll look at three particular examples where we see that generally acoustic models are more prone to make mistakes. So by acoustic model, I mean whatever it's your pre-trained plus the ASR model which Tahir was talking about. The most common type of error is the spelling errors. And since we know that we decode at character level and not at phoneme level, so it's bound to make spelling mistakes. For example, here I have shown a Hindi example where sunera can be, that particular word is misspelled. Another common form of error is what we call as homophones. So for example, here the original word was avsar, but our model predicted it as afsar. That's without the language model. ASR model predicted afsar. So these both are proper meaningful words, but in this context, this the second afsar doesn't make much sense. And the third problem is the problem which we incur a lot in Indian languages, is the problem caused by inflections. So there are a lot of words in Indian languages which have matras and other forms associated with it, which are very similar and very close by. For example, here we can see that hai and hai might not sound very distinct, but yeah, there are errors caused because of this as well. Yes, so I don't want to scare you with the formula equations here, but I will briefly cover what actually LM computes. Yeah, so a language model basically computes the likelihood of a sentence. And we all know by probability theorem that the likelihood is given by, if W0 to Wi is a sequence of words, then we can calculate likelihood by just multiplying the conditional probabilities conditioned on all the previous words. But we generally limit it to n-1 previous words, and that's why we call it a n-gram language model. So for example, here is an example of a bigram language model. Aaj sunehra avsar hai, where each the first word is conditioned on the start token, and I think there is some this should be reversed. Sunehra should be conditioned on aaj, and this should also be. So there is some errors in this slide. Yeah, but I think you got the concept that it is a bigram language model. Every word will be conditioned only on its previous word. Yeah, so when we see what is likelihood, we saw the formula, but in numbers you can see that if a sentence like aaj sunehra avsar hai is correctly written and we calculate the likelihood of this sentence, then we get a higher probability values. And if the sentence is wrong or is ill-formed, then we get a lower probability values. So we will use this idea of likelihood to actually score our ASR outputs. Yeah, now the question is, where do we fit language model in our ASR pipeline? So as we have seen that we start with a waveform which we pre-process into audio features, pass into acoustic model, and finally we get this logits. So as you can see, the logits are basically time versus character. So character is the total number of characters in your dictionary, versus at each time step you will get that many outputs. So this is the logits matrix, and this will give us the softmax output, which is actually the probability at each time frame. The point here is this: the output length the output length that you see here in the y-axis is not actually proportional to text length, but to audio length. And this is the issue with the CTC models. So what we do typically is we decode it. We decode this Logits matrix, and we try to find the in greedy solution. We'll just take at each time step. We'll take the best path. We'll take the best output, best character at each time step, and we'll keep moving on, as you can see here. Yeah. So this is D is the output at first time step, and then E, C, O, D, I. So this is how we evaluate using greedy decoder. But the thing is, now we are planning to incorporate language model here. We see there in this diagram that there could be multiple such paths. There are, in fact, exponentially increasing number of paths as we move across the time step. And there, the idea is that we'll use those some of the paths here to calculate the calculate score across all those paths, and also add LM score along with it. Yeah, so as you can see, for every such path, if we can calculate the probability of the outputted text, then we can get the total probability of that possible path. And that will lead us to what is called an exact or true solution. But the thing here is, this is a very costly operation. We have to go through every possible path in the Logits matrix and do LM decoding or LM score calculation on top of it, and then finally get the highest scoring path. So this is what we don't do in practice. Although this is the exact solution, we do kind of a compromise, which is called as beam search. So in beam search, I'll quickly explain this part. The idea is that we will only select the n best characteristics. So for the first time slice, we'll select the, for example, if beam size is 2, we'll select only the 2 best characters, irrespective of the total number of characters that we output. Yeah, and for example, at step 2.5, we'll rescore text outputs with the language model, and again prune on the basis of beam size. So at step 2.5, you can see that only H and E are left. And we'll do this, continue doing this, keeping a fixed beam size of n, and we'll get n beams at the end. From those n beams, we'll select the best path, and we'll get the final output. Yeah, now coming to the tools that we use for beam search decoding and along with language model. So there are 2 popular tools. One is a very recent PyCTC decode, and one is a flashlight based beam decoder, which are very popular in industry. So PyCTC decode has some advantages, like it has support for hot words. What are hot words? Hot words are, for example, if I have a separate domain and I want to include some words of that domain into that domain knowledge somehow into my ASR system. So we can do it by manually explicitly pointing it to those list of domain words, and it will give higher probability to those words, and in the end will give it will try to include those words as predictions. So those are hot words, and PyCTC decode has support for hot words. The second thing is, PyCTC decode is much easier to set up and experiment with, since it's a Python based library. It also has direct support or official support for Hugging Face speech models, Nemo speech models, and many other standard speech libraries. But on the downside, it is slightly slower than Flashlight decoder. Also, it doesn't have support for neural language models. So what are neural language models? We have not covered that. It's kind of, instead of using statistical language model, n-gram language model to get the scores of a text, we use a neural network to get the score of the text. So yeah, but that seems to be a very recent and very, I mean, people are trying out various types of language model, transformer language models and all. So PyCTC decode as of now doesn't support that. Flashlight again, Flashlight is a very popular library. The most important thing, it has support for neural language models, and it is extremely fast in decoding, and there are much more configuration options as compared to PyCTCD. But the one issue is Flashlight is mostly meant for research purpose. It's a library released by FAIRSEC. Initial web-to-web models, they have released models in Flashlight. So it's a rapidly evolving library, but sometimes newer versions are not backwards compatible. So something we have to keep in mind. Also, the official documentation doesn't have support for Hugging Face models or NeMo models. So that is, that we have to work around. If you want to integrate that we have to work around. Yeah, now coming to actually the code part, or how to actually use it along with ASR model. So it is basically, I'll cover it in two parts. One is the training part and the second is the decoding part. So the first step is to create ARPA file. ARPA file is nothing but just it keeps the probabilities of all unigrams, bigrams, trigrams, whatever order we have selected. So all those probabilities of the entire corpus, it keeps in a ARPA file. So as you can see that the first thing that it asks for is the order, which is the ARPA order. This is again, the number of n-grams we want it to evaluate to. So for example, we can have, if it's a bigram model we want to train, then we can keep ARPA order as 2. This is temp prefix, which is the temp intermediate directory. Memory is related to how much memory consumption your CPU will have, your model, when you're running on your system, it can allow. Then you provide the sentences, the corpus. The corpus is sentence split text file. Then you also provide options like pruning. So I will not go in detail, but these are some advanced options, and you can get more information about these parameter arguments on the official KNLM web page. So first you create ARPA file, then you filter from a lexicon. So what are lexicon? So typically a corpus will have millions of words. What we do essentially is, once we create an ARPA file from all those millions of unique words, we'll filter it from top keywords. So we'll create a vocabulary from the same corpus of top keywords, and then we will filter the ARPA file with those top keywords. So yeah, so it's a very straightforward command. You just filter it, you provide the vocabulary of top keywords, and you get a filtered ARPA file. Then you do quantization and binarization, where basically you quantize it to 8-bit, and so the model will be much smaller in size. Yeah. Then the second part is actually using this language model in a decoder. So I'm showing here the example of using it along with PyCTC decode. You provide it the vocabulary, which is the character vocabulary. You provide the KNLM model path and the alpha and beta. What are alpha and beta? So these are hyperparameters that we tune on a validation data set. Hyperparameters related to how we score language models. Alpha is the weight that we give to the language model, and beta is what we use for giving a penalty for a longer sequence. So if we have a negative beta term, it gives a penalty to longer sequence. If it's a positive, then it prefers a longer sequence. So yeah, more details can be found on the PyCTC decode web page and the website and their GitHub page. Yeah. So then we decode by simply using passing the Logits to it, and we get the text as an output. We can also decode with hot words. Just provide the hot words and the hot word weight, and you get the text as an output. Yeah, so these are some numbers. So here we'll see that actually adding a language model comes at a very cheap cost, because we just need an unlabeled corpus, and then we train it in an unlabeled way, unsupervised way, and we see that we get a fairly good decrease in WER. So this is from our paper, and we see that on average 28% reduction we got by just including a 6-gram language model. So what's the future scope with respect to language models? Definitely what we want to explore is neural language models. We also want to try much better integration of language models. Now we are just using it for scoring. We want to try how we can fuse it in a better way, fuse it with the, fuse the hidden states directly in the model itself. And maybe we may also try this end-to-end training with LM. Although currently the beam search decoder is this path of getting to the beams, getting output from the decoder is not differentiable. That's it. Thank you.